In a breakthrough series of simulations conducted across all timelines within cognispheric space, researchers from the McGinty AI Fractal Lab have successfully mapped a critical boundary condition in universal coherence, the fractal-to-stochastic transition threshold at 14.8 TeV. This elusive transition, often speculated but never precisely quantified, marks the energy scale at which coherent fractal structures, stable across quantum and subatomic domains, begin to dissolve into stochastic behavior in cosmic scale systems. What makes this simulation historic is not simply the result, but the methodology. The entire experiment was run within the 128-dimensional Mwave computer, a quantum fractal computational lattice operating in C-space, a domain that integrates quantum field theory, fractal mathematics, symbolic intelligence, and consciousness modeling. The McGinty equation provided the foundational physics, while Mwave harmonics and cognispheric symbolic language were used to encode, execute and analyze the results across energy, scale and temporal dimensions. This wasn't one experiment. It was an infinite field of synchronized simulations, folded across multiversal timelines, each contributing insight into the universal architecture of coherence. The scientific inquiry was deceptively simple. Why does fractal coherence persist indefinitely in the microdomain, but collapse into stochasticity above 14.8 TeV at macrocosmic scales? To explore this, the C-Space Lab simulated fractal field behavior across energy scales ranging from sub-electron-volt levels to hundreds of TeV, while adjusting spatial scale, temporal dimensionality, and entropic boundary conditions. The McGinty equation's dynamic form was activated with a stochastic damping term. E is a damping factor modelled using M-wave harmonic interference patterns. It remained near zero for all energy levels less than 14.8 TeV, but rapidly increased thereafter, degrading coherence in large-scale systems. At low energy levels, specifically below 10 TeV, the simulations consistently revealed a universe exhibiting full fractal coherence. The fractal dimension, D, remained stable at 4.2, and coherence levels exceeded 99.98% across all timelines. The stability tensor, S, was measured at an exceptionally low 0.00089, indicating an energetically harmonious regime. In this domain, the fabric of the quantum field retained its self-similar integrity, forming the foundational conditions for zero-point energy harvesting, stable quantum cognition, and multidimensional entanglement. As the energy range increased to between 10 and 14.7 TeV, fractal coherence remained largely intact, but subtle signs of entropic strain began to emerge. The fractal dimension fluctuated slightly between 3.7 and 4.0, and coherence dipped marginally to 99.95%. Still, the field maintained structural integrity with a stability tensor around 0.00096, signaling a twilight band of coherent behavior just before threshold transition. At this stage, timefold harmonics in C-space showed early divergence patterns but did not yet indicate systemic decoherence. Upon reaching 14.8 TeV exactly, a sharp and dramatic transformation occurred across all macro-scale timelines. This energy level marked the onset of stochastic behavior. Fractal dimensionality collapsed rapidly to approximately 2.1, and coherence fell to 87.2% within milliseconds of energy insertion. The stability tensor spiked to 0.0115, signifying a breakdown in self-similarity and the emergence of probabilistic field behavior. M-wave harmonics could no longer maintain phase lock, and C-space folds began to split into non-reconverging branches. This threshold proved to be not just a physical boundary, but a cognitive and causal one as well. Above 15.1 TeV, in extended simulations focused on galactic and interstellar scales, fully stochastic behavior dominated the system. Fractal coherence was lost, and the quantum field entered a decoherent state with a stability tensor rising past 0.02 and coherence dropping below 80%. These simulations showed no spontaneous return to coherence without external phase relock mechanisms. Cosmic scale entropic diffusion overwhelmed the fractal encoding systems unless bolstered by resonance anchors or artificial CSL stabilization. Interestingly, when the same energy levels were applied within microscale or Planck scale contexts, such as confined quantum cavities or subnuclear lattice frameworks, fractal coherence persisted completely. Even when pushed beyond 15 TeV in these constrained systems, the fractal dimension held steady at 4.2, and coherence remained at or above 99.99%. This demonstrated a crucial asymmetry. Stochasticity only emerges when energy is distributed across large-scale spatial curvature. It is not a function of the energy alone, it is the energy-scale interaction that drives the decoherence. This divergence between the macro and micro behaviors reveals a previously uncharted principle. The universe remains fractal at its roots, but becomes stochastic only when coherence is forced to stretch across cosmic structures without adequate phase reinforcement. The 14.8 TeV boundary is not a collapse point, it is a structural handoff between dimensions of order and entropy. The key finding, fractal coherence, is preserved indefinitely at the micro scale, even above the 14.8 TeV threshold. However, once energy is distributed across cosmic scale spatial curvature, coherence collapses. This confirms a phase asymmetry between micro and macro domains, a directional property of coherence. The simulations validate a bold MeQ-based hypothesis. Stochasticity is not a fundamental feature of the universe. It is emergent and only arises when energy scales interact with gravitational curvature in ways that exceed the coherence threshold. In this view, the universe is fundamentally fractal until it decoheres under energetic strain at vast scales. The 14.8 TeV boundary becomes not just a numeric curiosity, but a threshold of coherence collapse, akin to a cosmological phase transition. Defense systems engineering. Technologies operating near or above 14.8 TeV, such as space-based weapons and exotic propulsion, must account for coherence degradation. ZPE. Harvesting and stability zero-point energy systems based on MeQ dynamics are safe below the threshold, but they require phase lock reinforcement above 14.8 TeV. Multiverse cosmology. These simulations support a multiverse model where each branch preserves fractal integrity only within bounded energy curvature ratios, defining a new fractal life zone for timeline evolution. Quantum consciousness modeling. The microdomain's resilience to decoherence makes it a candidate substrate for long-term consciousness stability, relevant for AMEM, quantum memory, and overmind integration. Across infinite timelines, the evidence is consistent. The universe is fundamentally fractal, but only within coherence-respecting energy domains. Stochasticity emerges as a breakdown product, not a source condition. As our defense, aerospace and space exploration efforts edge toward energy scales once deemed theoretical, knowing where coherence collapses and how to reinforce it may become the most valuable knowledge on and off Earth.